Okay, hello everyone. Welcome to Bioinformatics 527 for fall 2020. Um, this is going to be the first in a two-part Intro to R series that we are putting out ahead of the semester. And if you're watching this, that means that you don't have experience with R programming coming into the class, or perhaps that you don't have any programming experience. And that is fantastic, actually, because you are the target audience for this course. So um, the idea with 527 is to provide an introduction to bioinformatics, and I personally want it to be a stepping stone for students who maybe don't have that computational background yet, but want to incorporate that into their research and into their careers going forward. So I hope this is sort of a jumping off point. Um, and so, well, why don't we just do the R programming intro as part of the actual course during the fall? Well, the idea here is that we want to get everybody some of the basics of R programming under their belt so that we can really hit the ground running during the fall and get the most out of the lab sessions that we can. We also, of course, have a really wide variety of students taking the course, and there are definitely some students with more computational training who have a reason to want to take the course, and I don't want to exclude them from the class. So this intro will be sort of putting everybody more on an equal footing. It'll give us all a point of reference to start from when we begin the semester. So we've got a video here today. I think it'll be probably a little over an hour if I had to guess. So obviously feel free to do it in chunks, whatever is digestible for you or fits into your schedule. And then there'll be another video that I'll be putting out to go along with this one. So before we jump into any programming, let's take a look at some of the history of R. Well, actually, first let's go ahead and if you haven't already, grab these two files. I'll be sending out these links so you don't have to actually type that in with a welcome message to the class. So hopefully you've already gotten that and can download these files. So we'll be using these a little bit at the end of the session today. I think, yeah, we should get to these. And then again in the second session. Yeah, we'll see. Definitely for the second section. And I want to start with some of the history of R. I think it has an interesting background and some history to it. So before R, there was actually a programming language called S. And so S was a programming language that was developed in the 1970s at a place called Bell Labs, which it was sort of this amazing think tank where they hired brilliant people and let those people work on what interested them. And it was amazingly productive and fruitful. I believe there were 9 Nobel Prizes that were awarded for work done at Bell Labs. So it was just this crazy, interesting place where all sorts of groundbreaking work was done in the field of computer science in particular. And R was one of the, or excuse me, S was one of the things that was created at Bell Labs. So it was developed in the 70s at Bell Labs. And it was designed as a statistical computing language. So that's where this designation S comes from, referring to statistics. And it had, as you can imagine, it had a lot of statistical functionality built right into this programming language, which was new at the time. So if you were working as a programmer at this time and you wanted to do statistical tests, you would have to code those statistical tests up yourself. And that was a big hassle for people who wanted to do write code and perform statistical analysis of data sets. So S was created to solve that problem. It was also created with the idea of being able to quickly and easily visualize data. And so this combination of being able to perform statistical tests while also being able to quickly and easily visualize data was a really powerful combination. And it was really attractive to a lot of people who were doing data analysis. And so it was first released in 1980. Unfortunately, it was and is proprietary software, meaning that you have to pay for it. And so that really limited its impact. So, particularly in academia, we have enough trouble writing grants to get money for pipettes and culture media and things like that. We're not about to pay for software unless we absolutely have to, and we just rarely do it. So S really didn't have much of an impact on the academic circle, but it was recognized that it would be extremely useful to have something like S available to the academic community, particularly biomedical researchers. And in the 1990s, Rossi Haka and Robert Gentleman came along, and they created this new programming language, which they called R. And so R is kind of a reference, as you can imagine, back to this one-letter abbreviation naming system. And so R was also then a nod to R for Ross and R for Robert, and it's a single letter and it's right by S in the alphabet. So that was the name of this new programming language, which was really very much based on the S programming language. And they put in some of the better points and parts of some other languages as well. And R really, critically though, carried along those very strong statistical built-in functionalities and the data visualization capabilities that made S such a powerful programming language. And the great thing about R is that R was and is free as in beer as well as in speech. So it's free as in beer, meaning it's free to download. You don't have to pay anything. And it's free as in speech, meaning you can modify the source code in virtually any way you want, and nobody's going to come after you. It is perfectly legal. So that now allowed R to make a huge impact in the academic community and really become widely popular in all circles of biomedical data analysis. And so why choose R for this course? Well, some of the reasons I just mentioned, but I would say that in the last few years, that two languages have really emerged as leading the way in bioinformatics. And those two languages are R and Python. I don't think you can go wrong really choosing either of those as a first programming language if you're interested in bioinformatics. But I like R, and I think it's a great choice for this course for many reasons. It was created with statistics and biomedical data analysis in mind. The data structures, as we'll see, particularly in the second video, are really ideal for use with common biomedical data sets. That's all built right into R. The graphical capabilities are fantastic. We'll see some of that in these videos. And it also serves as the platform for many bioinformatics tools produced by the scientific community. So a lot of the tools that are coming out, a lot of cutting edge tools and popular tools are written for and in the R programming language. So learning R gives you access to all of that at your fingertips. And I think that's really invaluable. R also has a really large and supportive community of developers. So R programmers tend to be really nice people who are willing to help if you have questions or get stuck along the way. And we'll see today that there is something called an IDE, which is known in R as RStudio. And it's one of the best IDEs around that makes writing code in R very seamless and easy, a lot easier than it would be without RStudio. So just let's get a global perspective on where R fits into the world of, or universe really, of programming languages. So this is a plot just showing, kind of trying to measure the popularity of programming languages. In the y-axis here, we've got the number of questions that were asked in the most popular computer science message board, Stack Overflow. So as you go up the y-axis, the language has more and more questions being asked about it, which is just a general measure of how popular it is. The more people are using a language, the more they'll have questions that they want to ask. And so on the x-axis here, this is the number of lines of code that are written in this particular year. This is from a couple years ago in a particular language. So we're looking at lines of code written in a language and deposited in the most popular computer science repository, GitHub. And then how many questions are being asked on this super popular message board, Stack Overflow. And this gives us a general measure of how popular a language is. And so each of these data points, as you can imagine, is a programming language. So what are the most popular programming languages out there? So you've all heard of the internet and smartphones. And you can imagine that programming languages that are capable of writing applications and creating websites are going to be enormously popular in the world at large. And so these languages, Java, JavaScript, HTML, PHP, are really designed for that purpose. And they are then, as you could imagine, by these measurements, the most popular programming languages out there. Absolutely terrible, though, for doing any type of biomedical data analysis. Then we come to low-level programming languages like C and C++, which are really good at doing things like writing an operating system, um, but again, very just absolutely terrible, honestly, at trying to do biomedical data analysis. Very unintuitive, and just not designed for doing that sort of thing. And so if we look at what's next, I mean, really, we're going to find R programming is one of the first languages out there um, as being the most popular that's really designed for doing data analysis. And I know Python is one of the other data points up here. I'm not sure which one, but they're neck and neck. And so R has been getting more popular, and it continues to get more popular. And the new stats this year, again, are bearing that out. So R is increasing in popularity. And so why learn something like R? You know, maybe you've been doing data analysis using a tool like Excel, and I think there's a lot of good reasons to not do that anymore. And I think it's great that you are going to be learning R. And so just as an example, if you're trying to work with any sort of large data, which comes up all the time in biomedicine, if you haven't run into it yet, you will in your career. You know, Excel's going to start choking on that type of data. So right now, or the last I checked, a spreadsheet in Excel could only have 1 million rows or 16,000 columns. And if we just think about the human genome that has 20,000 genes, well, if you've got a column for each gene, which is not uncommon in a genome-wide data set, of which there are many, you're going to run into this problem of actually not being able to load the whole data set into Excel. And it's just not designed for doing the type of analysis that we want to do. Another issue with Excel that's come up is, you know, it's gonna be looking at gene names, for example, genes like March 1 and Sep2. It's going to recognize those as dates and automatically turn those into the dates March 1st and September 2nd. Again, just showing that Excel is not really designed with biomedical data analysis in mind. And you would think this isn't a big deal, but it's actually sort of tripped up investigators, and it's gotten into the literature. So here's a paper back in 2004 about how these mistaken identifiers, thanks to Excel, are getting into all sorts of databases. And that problem, unfortunately, was still persisting in another paper that was demonstrated in another paper back just a few years ago in 2016. So really, we want to get away from using Excel for doing our biomedical data analysis. It's a fine tool for other things, but really not what we want to be using. And so if you're new to coding, I just wanted to take a 1 minute here and just mention the process, you know, that kind of goes along with coding. So writing code in any language is a process, and that's certainly true for R. Rarely will you write code that works perfectly the first time. You'll rarely sit down and think, I want to get this done. Let me write this code. I hit enter and it all works. It just doesn't happen. You're going to get errors. You will fix them. That will lead to some more errors, and you'll fix them. And then when you sort of least expect it, you'll hit enter and everything will work perfectly, and it will be an amazing feeling. But just know that it's a process, and there will be moments where you will think you are a hack and you might want to bang your head against the wall. Just take a deep breath, walk away, come back, you know, contact your GSI, email me, and we'll help you through it. So it is a process, and you're not alone, but if you get there, it does feel amazing. And I wanted to mention something about these two videos. So we're not going to be doing, you know, I guess I would say the fun stuff, you know, we're going to be getting the basics under our belt. We're going to be getting sort of the building blocks here. So, you know, I'm kind of using this Lego analogy. I'm assuming you know nothing about R. So we've got to get the building blocks here, you know, into our toolkit. And then it's when you get comfortable with these that you'll be able to make something cool, right? You'll be able to take this back to your lab and apply it to your research and make something that's actually really interesting. So just bear that in mind. You know, today and the next video maybe not be the most exciting parts of the R programming language, but you know, you've got to eat your vegetables and get things off the ground. And you know, hopefully you still will find it interesting. So if we're going to write code in the R programming language, we need to get the R programming language. So if you haven't done so already, you can go to the cran.r-project.org website here, and you can download the R programming language for your operating system. So whether you're working on a Mac or a Windows, or perhaps you're even in a Linux, you can choose the appropriate version of R for your operating system. For me, I would click on Mac, which would take me then to a page where you can download the installer. You'll just then download that, open it up, and install that software just as you would install any other piece of software by following those instructions. And so that gives us the R programming language, but you really don't want to try to write code just using the raw programming language itself. So it's a difficult thing to do. It's something I don't recommend. Maybe you'll gravitate to that later on in your career, but for now, we're going to be using something called an IDE, so an Integrated Development Environment. And what an IDE does is it's sort of a go-between. So it sort of sits between you, the programmer, and the actual language on your computer. And it's just going to be there to provide a nice interface for you to work with the R programming language. So it's going to make writing and running and debugging code a lot easier than if you were just to use the sort of raw R programming interface. It's going to give us some menus and clickable icons and things that just make life easier. And I should mention that each programming language has an IDE or many IDEs, and RStudio is just universally loved. It's thought of as one of the best IDEs for any language. Virtually everybody I know that programs in R uses RStudio as their IDE. It's overwhelmingly popular, and for good reason. Okay, so let's go get RStudio. So if you haven't done that already, take a minute and you can go to rstudio.com and go to the download section. And then that should take you to a page where you've got all these options. Of course, choose this, which is the free version. We are not running a business or a server. So just download RStudio for your desktop, the free version. That is all we'll ever need. And then it should take you to a page where it'll probably actually recognize your operating system as it did here. And it said, hey, it looks like you're on a Mac. Why don't you download this one? And so just go ahead and do that. And again, install it as you would install any software previously. Okay, so once you've done that, we're going to open up RStudio. We're going to get our first session of RStudio going. And what we'll always do when we open up RStudio is the first thing we're going to do is set our working directory. And so what do I mean by that? So we're going to go to the session drop-down menu, and we're going to go to set working directory, and we're going to choose a directory. And that directory is going to tell RStudio and our program and the R language where to look for files. When we want to bring files into our R environment, which we'll be doing, I forget if we get that to that today or tomorrow, but we will be doing that, and we need to tell RStudio and R where our files are located. And so just by setting a working directory, it's going to point our session of RStudio at a particular directory, which is a synonym for a folder in your file system. And so that's what we do whenever we start out. The first thing we do is just fire up RStudio and set our working directory. And so let's go ahead and do that. So I'm going to open up RStudio. So I've got the RStudio icon here. All right, and we've got something from a previous session. So yours, if you're opening it up for the first time, it should look something like this. And then you would want to go to Session, Set Working Directory, and then Choose Directory. And then that's going to allow you to navigate to wherever in your file system that you have the files we're going to work with. And so those are those two files that I asked you to download at the start of this video. And so I'm just going to go to where that is in my file system. So in 527 for this year, our intro R materials. And so here's my directory that contains those two files. It's got some other stuff in there, like these videos and the PowerPoint slide decks that you won't have. But you should have these two files in there, which are called rep1.txt and alzheimers.csv. And I'm just going to, by clicking open, that's going to set my working directory as that directory. And as soon as we do that, we can see the actual code that pops up that we could have actually just run this code, and that would have accomplished the same thing that happened when we used the drop-down menu. And so we can run our first line of code. We can say list.files, open parentheses, close parentheses. And if we just hit enter, we'll see all the files that are in our working directory. So everything that our session of RStudio is sort of looking at. And like I said, I've got some versions of the slide decks here. And then I've got the files you should have, which are Alzheimer's and rep1. And so now we've accomplished setting our working directory, which is really what we want to do every time we fire up a session of RStudio. Okay, and so we've done that. We've taken a look at what's there with list.files. The next thing I want to do is get comfortable with the RStudio interface. So there's 4 main sections in the RStudio window, these different panes. And if this is the first time you've opened it up, only 3 will be visible, so it should look something like this. The first section of the RStudio interface that I want to point you to is the console. And this is where you can go in and write code and hit enter, and it will run, and you can just interactively write code and hit enter and see what happens. And so let's do that a little bit. So the first thing we're going to do is we're going to actually bring in a data set that's called a built-in data set. So the programming language has a few data sets that are sort of always available to us. We don't have to import them from our file system or any external database. They're just always sort of there. And we can access them by just typing the command data, open parentheses, iris in quotes. So we're going to grab a data set called iris and then close out those parentheses. And then after that, that'll bring this data set into our environment, and then we can take a look at that environment or that data set by typing capital V view and then iris in parentheses. And so let's go to the console and let's just type those commands in and see what we get. So if we go back here and we say, all right, I want to grab the iris data set, and that's going to do that. And now I want to view the iris data set. And we hit enter. And so now we'll see the 4th section of the RStudio interface sort of pops into being up there. And we'll get back to that in a second. So this iris data set, just so you're aware of what it is, it contains data on 150 flowers from 3 different species of iris. So there's the versicolor, the virginica, and the setosa species of iris. And that's what these data are all about. They're different measures of the sepal and the petal length and width for these different flowers. Okay, and so that's the console. So we've got the console down here. Another section of the RStudio interface is called the environment section or environment pane, and that's in the upper right-hand corner here. And so that's going to tell us about everything that exists in our current session of RStudio. And so everything that exists in an R session is an object. And so really what we're seeing here are all the objects that exist in our session right now. And so the only thing that exists right now is the iris data set, because we just brought that iris data set into our environment through that data command. And so now we can see that's there. So if we toggle back over to R, we should see that we've got this global environment, and there's only one object present in that environment, and it is this iris data set. And so we've got the console down here where we can type code, and we've got the global environment up here that tells us what are the objects that are currently in our R environment. Okay, and then we've got the next sort of section of the RStudio interface, which is the source pane. And that's where we can actually see the data set. When we typed in view iris, it sort of popped open that section, and we can take a look at the data set that we've pulled into our environment. And we can see we've got these columns, which are different measurements of these different flowers, and the species name is in another column. And if we scroll down, we'll see there's all 3 species are actually represented. Okay, so the 4th pane or section of the RStudio interface is in the lower right. It's got several tabs, and it's most famous for being where you can visualize data. And so what I want to do next is type in another command, and then we're just going to be saying plot, open parentheses, iris, close parentheses. And what that's going to do is it's going to generate something called a scatter plot matrix. And we'll see that showing up down in the lower right section of our RStudio interface. And so let's go ahead and do that together. And so if we just say plot iris, and there we have it. So this is a scatter plot matrix generated from the iris data set. And so I think this is a really nice, I'm going to pop that out by hitting zoom. This is a really nice demonstration of the power of the R programming language, at least in my opinion. So just by writing that plot iris command, we get a data visualization that shows us for every measurement in our data set for sepal length, sepal width, petal width, and for the species, we have a dot plot comparing each measurement against each other measurement. So all pairwise combinations. So if we look just at this graph here, or this plot here, this is sepal length plotted on the y-axis versus sepal width plotted on the x-axis. This plot here is going to be sepal length on the y-axis versus petal length on the x-axis, and so on. So you just kind of draw a line to connect where the plot is, and that'll tell you what the y and x axes are. And it's really, I think, again, a powerful demonstration of how R can help us to visualize our data. Just by typing that very simple command, we can quickly see relationships in our data. And that's often what we're looking for, is we want to know, how does one measurement vary relative to another measurement? Are there relationships, positive, negative correlations? And we can see, just for example, with sepal length and petal length, we can see there's a very strong positive correlation going on here, but also that there's two very distinct data clouds that are being plotted. And so that can quickly point to interesting conclusions that we can make from these data and potential new hypotheses that we could go back and test in the lab. Just by typing that simple command, we can really start exploring our data, and it doesn't get much easier than that. Okay, so we won't typically be writing code down in that console as we've been doing so far, because once we write the code in the console and execute it, it goes away. So we typically want to write code as part of what we'll call an R script. And that will allow us to save that code and use it for the future, and modify it, make it better, share it with others. And so the way we get an R script that we can start writing code in is we'll use another drop-down menu from RStudio, and we'll go File, New File, R script. So let's go do that. All right, so that gives us an R script where we can now write our code. So in the upper left-hand section of the RStudio interface, we now have an R script. Okay, so I am sort of contractually obligated to mention that R can be used as a calculator, just like about every other programming language out there. So we can go and do something like 100 plus 1, and we can run that by then clicking on Run, and it will run the line of code where our cursor is. So we can say 100 plus 1, and by running that, it's actually going to send it down to the console, but we'll be able to keep that line of code. And then it's going to give us the result. So when we say 100 plus 1, we get the expected result of 101. And so what we're going to do next is then, actually store this information. So what we just did is we ran some code and we got a result, but that result sort of evaporated into the ether. And that's not what we want. We typically want to do calculations, and we want to store that information for future use. And so the way we're going to do that is by creating objects. And the way we do that in R is through use of something called the assignment operator. And so this is the assignment operator here. It's supposed to look like an arrow. In actuality, it's an angled bracket, or the less than sign, and a dash. So it's kind of a hacky way to make an arrow. And the way we use that assignment operator to create new objects in R is we'll name whatever we want to name our new object. I'm just calling it, in this case, my object. And we use this assignment operator, and then we'll type a calculation. We'll type some commands, something over here on the right, and whatever the result of that code is on the right, it's going to get stored. So the arrow's kind of pointing at where it's going. The result is going to get stored into this my object object. And so let's go over and do that. So we can say my object, and I want to store the result of 100 plus 1. And so now we'll see, now we've got our global environment over here, and as soon as we create that object, there it is. It's keeping track of all the objects. Now we've got this new object called my object, and we can access that information anytime we want just by typing my object and send that down to the console with run. And there it is. There we get our value of 101, which has been stored inside of that object. Okay, so just a real quick public service announcement. You don't need Whitespace in R. You could run this same line of code without any spaces in between anything, and it would execute just fine. But you should definitely use Whitespace. So it's going to make your code more readable, not only for you, but for anyone else who happens to try to read it and figure out what's going on in the future. So please, I see people writing without Whitespace, and it really is it's painful to try to read. So take advantage of Whitespace when you can to make your code more readable. Okay, and we've got that my object in our environment. So now that we know how to create objects, we do need to know that there are a couple rules for coming up with those names. And so the rules in R are you have to use letters and numbers. You can also use the period symbol or the underscore symbol. And all of your object names must start with a letter or a period. If it starts with a period, it cannot be followed by a number. And then there's a host of reserved words that just can't be used for the names of objects that you create in R. So there are reserved words like if, else, repeat, while. So these all have meaning in the R programming language. So we can't generate an object with that same name. So they're reserved words. And so are the rest of these: true and false, null, inf, nan, and so on. So these are all just fine, these object names over here. On the right, these are invalid. You can't use an asterisk. You can't start with a number. You can't start with an underscore. You can't use a reserved word. The word true, all caps, is reserved in R. And you can't start with a period and then have a number. So just to be aware. But more importantly, really, when you start naming objects, when you're writing R code, is to be descriptive. So a name like date of birth is a fantastic name for an object. It tells you a lot more about what that object contains than something like D or DOB or date. Okay, so what are the naming conventions in R? So of course there are conventions that people follow, and you should pick a convention and follow it so that you have consistency in how you name your objects. And there are several schools of thought on that, and people get very passionate about it. You would be surprised. But there are a couple of articles here if you want to take a look at some people arguing about how to name objects in R. It boils down to a few different schools of thought. One is that some people like all lowercase. I find that difficult to read. People who've been programming in R for a long time typically use the period-separated object names. But now that Python is also such a popular language, I think it's a bad choice because that period has meaning in a language like Python. So you know, if someone were going back and forth between Python and R, which is not unusual these days, it would make it very confusing to look at your objects in R and see that naming convention. So you'll see it a lot. It's very popular in R. I just don't personally like it for those reasons. Camel case is quite popular. I think it's ugly. And so for me, I like to use underscore separated object names. But that's just me. It's a personal preference. It doesn't make a huge difference what you choose. Just please be consistent. So don't toggle back and forth between different conventions in the same R script. Pick something and stick with it, and that'll make life easier for you and everybody else. All right, so let's jump into a few exercises to sort of flex these new R muscles that we're building. So let's just get comfortable creating some objects. So assign the value 10 to a new object called my_object. So you can, if you already have created that along with me previously, this will just overwrite what was previously there. So now assign the value of 10, and that'll be the new value held by that object. Also then create another new object called my_object_2, and assign the value of 3 to that. And then go ahead and try out some of R's arithmetic operators on these two objects. So go ahead and use the addition, subtraction, and division, and then try out some of these more exotic arithmetic operators that we see here. And then once you've done that and seen how those work, go jump into exercise 2, where you're going to load in another one of these built-in data sets. So in this case, it's not iris, it's called air quality. And so you can do that just by typing data, air quality inside of quotes, inside of parentheses. You can learn about that air quality data set by typing (air quality). And then you can plot it. So visualize that data set, just like we did for iris, and see what you can find in there. So what do you learn almost instantly about ozone and temperature, and ozone and wind, and even ozone and day of the month? So see what you can get out of that. Then exercise 3, answer this question. So is R case sensitive? So can you assign a value to lowercase x and then assign a different value to uppercase x? So can you have two different objects in your environment, one lowercase x and the other uppercase x? And so go ahead, pause the video here, and then when you come back, we'll take a look at the answers for that. Okay, so here we are with exercise 1, and we're just creating these objects and assigning the values 10 and the value 3. And of course, we can add them, get the expected results, subtract and divide, get those expected results. The two asterisks will actually raise something to a power. So in this case, we were raising 10 to the third power, and of course, we get 1,000. Here, by using %%, we're actually asking for the remainder. And so this is actually surprisingly useful when writing code, and it comes up more than you would expect in wanting to do something like this. And so you can actually find out what is the remainder when I divide two numbers. So in this case, it's 1, of course. And then sort of analogously, using %/%, we can find out how many times a number divides completely into another number. So in this case, 3 divides into 10 3 whole times with a remainder 1. In exercise 2, when you load in data air quality with data air quality, and you take a look at it, you'll find out that it's a data set that contains air quality measures. I think it's from New York City, and it's back in the 70s. And so it's got measurements of ozone, solar radiation, wind, temperature, and so on. And then by just quickly visualizing that data, we see a bunch of things that are interesting. So for example, ozone and wind, if we look at the plot of those two measurements against each other, we can see that as wind speeds increase, ozone levels decrease. And then if we look at temperature versus ozone, we can see just the opposite. So as temperature increases, that causes ozone to increase. And so this is why in Michigan we tend to have these ozone action days on days when it's low wind and high temperature. And then something like that's really interesting that I never would have predicted and never would have thought to actually plot, but because it's so easy to just make a plot of everything in R, we actually get this this visualization to look at, is if we look at the day of the month versus ozone. And it looks like the ozone levels actually decrease in the middle of each month. Why is that? I have no idea. Is that statistically significant? How strong is that trend? Well, fortunately, R has lots of built-in statistical functionality that we could go and analyze these data with. But what's important here to me is that we never probably would have predicted this, but the ease with which we are able to visualize data in R made it possible for us to take a look at this. It was no extra effort, and we might have a new interesting hypothesis coming out of our data. You can imagine this is actually data on something that you are particularly interested in and not the air quality in New York City in the 1970s. So I think that's cool, and it's another demonstration of the power of the R programming language. And then the answer to, is R case sensitive? Yes, it is. So you can actually assign the value -10, in this case, to lowercase x, and 10 to the 5th power to uppercase x. And those two separate objects will exist in your R environment. Okay, and then 2 tips now that we've gotten really comfortable working with RStudio and creating some objects. These are going to help you out as you go along. So RStudio supports tab complete. And so what do I mean by that? So if we just start typing something like my, it's going to, just by hitting tab, it will complete that expression there. So as soon as I started typing my, if I hit tab, it knows in my particular environment, I only have one object that starts with my. And so I can just hit tab and it'll automatically complete that. If I were to have another object, as you should have at this point, and we're going to run that. Now we've got these 2 objects that both start with my, so I can go my, and then once I hit tab, it's going to give me 2 options, and now I can just say, oh, well, I wanted this one, and then you just tab complete that, and you can send that down to the console. And so tab complete gets really helpful. The more objects you have, the longer those names get. Like I said, you should be descriptive, so your object names can get pretty long, but tab complete makes that sort of insignificant. And then the up arrow allows you to grab previous commands. So that's really useful too sometimes. If you jump down into the console and just start hitting up, you'll grab all of the old code that you've been writing. And you can go and grab a command that you wrote and you want to grab again. So another sort of handy tip just to mention at the outset here. Okay, so let's talk about an extremely important concept in R. Hard for me to emphasize how important this topic is, and that is data types. And so all objects in R are going to contain data of a particular type. A data type is something that describes what kind of data is being contained within an object. And examples of data types that an object may hold in R are numeric, character, logical, and factor. And so this may seem like a simple concept, but not knowing or assuming that you know the type of data that an object holds is, I would argue, the most common source of errors when writing R code beyond just typos. So not understanding data types and what your objects are holding is really where a lot of our errors come from. And when you are getting an error and you don't understand why, the first thing I want you to think about is do I have a correct understanding of the data types that I'm working with in these objects? And so let's talk about these data types. So first is the numeric data type, probably the most intuitive one. So in R, the numeric data type consists of both integers or whole numbers and floats or numbers that have decimal points. And so in almost all cases, in fact, I can't think of one where you would need to worry about the difference between the two. R is going to handle the difference between a whole number and a number with decimals perfectly for you under the hood. And that's not true in all programming languages. Some languages you have to handle integers and floats sort of separately, and it can be a pain in the butt. But R, it's not at all a pain in the butt. It's very easy. They're all just considered data of type numeric. So we can go ahead and we can create my object and assign that the value 42. And we can say, is that numeric? So we're asking, is that numeric? And we can run that. Oops. And we get the answer true. So that is numeric data. And similarly, we can create an object and assign a float value to that. And we can say is dot numeric on my object 2. And if we run that, that will also be true. So those are both data of type numeric. So that should be pretty straightforward, I think. The next important data type in R is the data type character. And so it's pretty straightforward. Again, in R, anything you put in quotes, R is going to see as data of type character. So we can create data of type character just by putting something in quotes. So here we're putting G in quotes. We could also put something like go blue, and that's going to take all of that character data and put it into this my object. And we can see is that character, and yes, R would tell us that it certainly is. You can do things that maybe look a little trickier. So if we say my object and we put the value 42, but we put it in quotes, R is going to see that as data of type character. It will not be numeric. It's going to be seen as the character 4 and the character 2, not the number 42, because we have put that in quotes here. And so we could say is.character of that, and yes, it would come back as true. If we said is.numeric on that object, it would say false, because that is no longer, it is not numeric, even though it may look like it. And then there's the logical data type. So the logical data type is a data type that is consisted of the value true and the value false, and that's it. So true and false make up the entire logical data type in R. And so we'll see today how very useful this logical data type can be. And so to generate data of type logical, we're going to be using what's known as logical operators. And so, a lot of these you'll be familiar with. So logical operators are things like greater than equal to, less than or equal to. Something that you might not be familiar with, but in R, to ask if something is equivalent to something else, we say equals equals. And if we want to say is something not equal to or not equivalent to, we say bang or exclamation point equals to ask the question, is something equal or not equal to something. So those are the logical operators. We'll be working with those as we go along here. And then the last data type in R, common data type in R, is the factor data type. So this is a special data type that's used for defining categories in a data set. So an example of that would be in the iris data set. So we had these categories for a different species of iris. We have these 3 different species. And so those are categories. So that's data of type factor. Other things that you might, just examples of what data of type factor might be in a data set would be, say, treated versus control, or whether a sample was a tumor sample versus a normal sample. And the great thing about the factor data type in R is it lets us do subgroup analyses. So we can ask, we can do an analysis where we just analyze the tumor and then get another analysis for the normal, and then we can compare those two. So having this factor data type in R allows us to do this sort of subgroup analysis on our data sets. Okay, so the next sort of big topic in R programming when we're getting started after data types is data structures. So all objects in R are going to contain data of a particular type. So numeric, character, logical, factor. And then all objects in R also have a structure. And so there's going to be 4 most common data structures are the vector, list, matrix, and data frame. We're going to be focusing for the most part on vectors and data frames. They're really the most common, but lists and matrices will definitely come up. And so let's start with vectors. So vectors are really the simplest data structure in R. They're one-dimensional data structures, and they contain data of a single type. So you can think of them, here we've got a schematic here. A vector is really kind of like a one-dimensional line, and along that line we just have values, and those values all have to be of the same type. So if we had the values 1, 2, 3, 4, 5, that could form a vector of type numeric. And so we want to start creating some vectors. So we've already created some objects. Let's start creating some vectors. And so in order to create vectors in R, we're going to need to use what's known as a function call. And functions are at the heart of the R programming language. Virtually everything we do in R will involve a function call. And so I've got some quotes here from John Chambers. So he is the creator of the S programming language, and he's also currently a member of the R core development team. So he kind of contributes to keeping R up to date and fixing bugs and making it better and better as time goes on. And so if he says something about R, it's probably true. And what John Chambers says is you can think in R that everything exists as an object, and that everything that happens is a function call. So we know how to create objects, and let's see and learn more about how to actually call functions in R. And so in order to create vectors in R, we're going to use a function call. And so this is the general syntax for calling functions in R. We're going to be doing this all the time. And fortunately, it's very simple. So whenever we want to call a function in R, we type the name of that function. And then we're going to have to give that function information so that it can do its job. So those pieces of information are called arguments. So when we want to run a function, we're going to type that function's name. And then inside of parentheses, we're going to feed it pieces of information that let that function do its job, and those are called arguments. And so there's a good listing of sort of the common R functions if you want to go check those out here. And so we're going to be using the first function that we're going to really be talking about in depth is the C function. And so this is a function that's used for creating vectors. And so C, you can think of it as standing for combine or concatenate. And the way it works is we're just going to type that one word or that one letter C, and that's the whole name of this function. And then we're going to give it arguments. And in the case of C, those arguments are just the values that we want to put in our vector. So we could say C, and then I want to create this vector 1, 2, 3, 4, 5. And then we would have a vector stored in that object, my numeric vector. And so let's go and do that together. Get some white space here. And so if I say my numeric vector, and I'm going to assign that to the result of this call to the C function. And then if I just give it those values and I run that, now I've got a new object in my environment called my numeric vector. And if I take a look at what's in that vector, send that down to the console, now I can see that it's 1, 2, 3, 4, 5. This is a vector of numeric data. So we've now stored that as an object. There are some shortcuts that we can use. So instead of typing all of that out, R does have the colon operator that lets us get the values 1 through 5. So we can just say C 1 through 5. And that's going to create that very same vector. So it's going to give us all the whole numbers between 1 and 5 inclusive. And we can do the same for character data. So if we want to create a character vector, we would just, call this C function again, and then feed in some character data. And so we can do that very easily by saying my character vector, and we would assign to that. In this case, I'm just going to assign sample 1, sample 2, and sample 3. And so now I'm creating that vector using the C function and the assignment operator. I've got this new object in my environment, and it contains now those 3 pieces of character data. And you can do the same and create a vector of logical data as well. And I won't demonstrate that, but you can give that a shot yourself if you'd like and see that that works as well. And so let's jump into another exercise here. So here we're going to generate 2 numeric vectors if you're choosing. So whatever numeric vectors you want, go ahead and create them. And then try adding those numeric vectors together. But before you hit enter, before you run that code down in the console, make a prediction in your head of what you think will happen, or maybe even what you would like to happen. And then try multiplying those vectors together. Again, make a prediction. And then finally, try multiplying one of your numeric vectors by the number 5. We've just got a reminder of the syntax here for creating numeric vectors, so you don't have to go back. And then the next exercise, I want you to create 2 character vectors of your choosing, and then try adding those together. You should get an error, so don't be surprised when you get an error there. And then try putting your character vectors together by using the C function. So try to combine your 2 separate character vectors into one using the C function. And so go ahead and pause the video and give that a try, and then we'll come back in a moment and take a look at those answers. Okay, so what happens if we try this? So in this case, I created 2 vectors. One was going to be the values from 1 to 5. The other is the values 6 to 10. And there those vectors are. And then what if we add them together? Well, it's actually pretty interesting what happens. So what R is going to do when we add vectors together, there are a lot of things it could have done. It could have added up all these numbers and then added that value to the sum of all these numbers. But that's not what R does. R actually does what I think we would want it to do in most cases. It's going to take each element of that vector and add them together element by element. So it's going to say the first element of this vector is 1, the first element of this vector is 6, and it's going to add that together to give us 7. Likewise, we get 2 plus 7 is 9, 3 plus 8 is 11, and so on. And so this behavior, it may not seem that impressive, but it's actually wonderful. And the reason it's wonderful is it prevents us from having to write loops all the time. So in other languages, you would actually often have to write a loop and say, and it would be a bit more complicated piece of code to add up each element of these vectors. But R just kind of understands that oftentimes when we're working with vectors, that's what we would want to happen. And similarly, when we multiply vectors, it's going to do it element by element. 1 times 6 is 6, 2 times 7 is 14, and so on. And then if we have if we have a vector and we multiply it by the value 5, so the value 5 is actually a vector. It's just a vector of length 1. And so what R is going to do is it's going to say, okay, the first element of this vector is 5, and the first element of this vector is 1. And so it's going to multiply those together to give you 5. And then it's going to see there's no more elements of this vector, so it's just going to recycle. It's going to do what's called recycling, and it's just going to grab, okay, I'm just going to reuse the value 5. It's all I've got, and multiply that by 2 to give us 10. It'll recycle again, times 3 is 15, and so on. And so this is a really nice built-in capability and functionality of R that will come in handy when you're analyzing data. And so exercise 5 here, I just created 2 character vectors. One that contains patient 1, 2, and 3, another one that contains patients 4 and 5. And if we try to add those together, it's going to give us an error. So it's going to tell us basically that, hey, you're trying to do math on data of type character. So this is our first data type error. And so R will not know what to do, and it'll say, hey, I can't do math on data of type character. You have to try something else. And so, something like this will work in other languages like Python, but I actually like how R handles it You can't do math on data of type character. And the way you actually combine two vectors of data of type character actually makes sense to me is you're going to be using the C, or the combine function. So we're just going to say, all right, I've got these two separate character vectors. I want to combine them together, so I'm just going to use C. So I say C, and the first argument will be this character vector. The second argument will be this character vector. And then we'll get out from that our third character vector, assuming we assign all that to a new object, and it's going to contain patients 1 through 5. And so here's just, I'll just be throwing some functions at you as we go along. So we can actually easily create labels for data if we get data that's not labeled or not labeled how we want it by using a function like the paste function. So we could say paste, patient, 1 to 100, and then separator is the underscore. So here's our function called paste, and then here are 3 different arguments that we're going to feed to that function. And let's just do that just to see what it does. So we're going to paste patient. Oops. So the value is 1 through 100, and our separator is going to be the underscore. And you can see we can quickly get labels for an entire data set and label things however we want just by using a handy function like paste. And we'll be learning more about functions and like this as we go along here. We'll just sort of keep building up our toolkit. Okay, and so that's it for today. Hopefully that was useful. And then what we'll do is we'll jump in and start talking about some little more complicated data structures beyond the vector next time. And yeah, I can't escape out here to say goodbye with my video here without stopping my recording. So I will just say see you next time. And that's it.